excuse me, when we're talking about independent versus dependent events, it's a very easy thing to understand because you probably already know how to do this. You've probably done it before.
The probability that you've done it is high.
Now, let me ask you this. If I'm going to draw 2 cards, and I want to do the probability of drawing 2 cards, and I'm going to put the first card back in the deck. What will be, so this is going to say the probability with replacement, which means I put it back in there. And I want to say, what is the probability of going Jack and a 4 with replacement? So the probability of getting a Jack is what? 4 out of 52.
1/169.
And then what's the probability of getting the 4? 4 out of 52. Since I put the card back in the deck, the amount of cards within the deck didn't change. So going Jack 4, did that have any bearing? Did the second card depend on the first card?
No.
No. So was that an independent or a dependent event? They're independent of one another. The reason that they're independent of one another is because of the idea that I said with replacement. So what happens here, to get your to go of an independent event, all you do is you take the 2 probabilities and you multiply them together. You already did the simplify out and you get, was it 1/169, I think?
Yeah.
So these here, since these are independent events, because I had what we say with replacement, the amount of cards in the deck didn't change. Think about the lottery. The lottery, if you're doing this, the lotto, there's 1 out of 56. If one of the ping pong balls come out, how many are left in there? 55. Does that become independent or dependent? Dependent. Yeah.
Are you multiplying them because it's this new independent?
Yeah.
Okay, so if it's independent event, then it's multiply.
Correct.
Okay.
If you think of it, you've also worked with independent events in what is it? Not genome. Regressive genes, I think. We were talking about eye color. Didn't you guys do like the square? Where you multiply them first? What's that? Yeah. It's something along those lines where if you had another way of looking at it, yeah, there's other ways of going through like the probabilities of all those things occurring. Another easy way to think about it, another easy way of thinking about is you flip a coin. If you flip a coin, how many options do you have? 2. Heads and tails, right?
On the side. I think that's on.
That's a Twilight Zone episode where it lands on the side and then you got to hear everybody's thoughts.
So what happens here if you want to go the probability of flipping a coin, you want to flip a coin 3 times and go heads, tails, heads, is each one of those flips independent of the other?
Yes.
They are.
Oh, wait.
They're independent because you're flipping it, looking at it, flipping it, looking at it, and going each time. Each time you go through it, it's either going to be heads or tails. So what's the probability of getting heads? 1 out of 2. What's the probability of getting the tails then? And then what's the probability of getting the heads again? So you wind up with 1/2 times 1/2 times 1/2. So to get that to happen, you have a 1 in 8 probability. So you start to see the idea of like a winning streak. It starts to become more and more difficult. Just the theoretical probability of a long winning streak. I think in baseball, what's the record for winning streaks? It's like 22 or 23? I think I want to say it's 23. Or like the major league record for wins.
No, that's hockey. It's the Hawks.
The Hawks were, they went score. The hockey's a little bit different because you can tie. In baseball, where you're either going to win or you're going to lose. Okay? And I know that there's other things thrown in there about the whole idea of, well, one team is obviously has better skill than another team, so that can get factored in. But I'm just talking win-loss.
Isn't basketball 23? Rockets. The Rockets did a few years ago.
I'm busy with the deck of cards right now. But let's just say you start to think about the idea of just winning 10 games in a row. It's either going to be you're either going to win or lose, so it's 1/2 to the 10 power. It's a really, really, really faint probability of just winning. So you start thinking about the improbability of the win streak. It's really difficult to do. Okay? It is really difficult to do. Now, the difference between this, well, your independent events, when you're talking about independent again, if one event is an occurred, the second event isn't based upon the first event, that's what we call independent. Flipping a coin, registering it, flipping a coin, registering and going on. So in order to find those probabilities, if you want to find this and something else, you take the two separate probabilities and you multiply them together. Okay, you get that. It kind of works the same way with like the Wheel of Fortune. When you spin the Wheel of Fortune, you get a certain dollar amount, right? So let's say you want to find the probability of landing on something that is greater than $500. And then on your second roll, you're going to go bankrupt. So if you want to think about, you want to go probability of greater than 500, and then you want to be bankrupt. Why you want to be bankrupt, but you can't. Here's my spinner. So, probability of the number being, your dollar amount being greater than 500, it's already labeled with an A.
Oh.
So it helps a little bit.
8 out of 8 over 1 over.
So, 8 out of 24. Now, are these going to be, are the spins themselves independent of one another?
Yes.
It's not like they're taking one out. Okay. How many bankrupts are there? 2 out of the 24. And what you're doing is you're simplifying it out right away, which is fine. You can simplify it, make your life easier, or if you want to just put in your calculator, use the fraction bar, it'll give you the same answer. What'll happen is you get 1/3, and you get 1/36 of the probability. So here's my first spin. Still spinning.
I didn't know you get that.
Nobody mentioned
Oh, it
what's
lands on that
happening.
line? It's like right in the middle.
300.
I got $700. Yay! Win!
It always came back to where it started.
Don't mess with something that doesn't work right.
I should do
Does
it.
that work at any class?
I don't even care what does they come back and they do a cool thing. That's good.
You guys don't see something like this.
I think this is
White
cool.
outline covering the warriors.
So you've never used the spinner in class before?
No.
You've never come up to the board and hit the spinner?
Oh, man.
So what, you just put, does it always land on the line?
No.
I'm gonna say green.
Whipped green.
All right, so let's think of this. Let's number it. 1, oops. Well, this was supposed to work.
What's happening?
I don't know. Spinning faster though. I don't know what we're doing anymore. Well, I was going to write in a bunch of numbers and talk about probabilities of odds and evens with different colors, but hey, whatever. What?
Nothing.
You guys have never used the spinner in class before?
Nope.
That means you've never seen the dice with your face on it, have you?
No.
No. Do
I
it.
have to make it. I didn't make it yet.
It's Morgan's picture.
Yes.
That one, yeah. No, I can actually make dice and have your face be the face of the dice.
Kayla, what if you ask for her ponytail signature?
I'll make it for tomorrow.
What is that? Oh, the hair.
So let's look at dependent. A dependent event is a little bit different. Again, you have done this before. A dependent event now is the same idea, where I want to talk about the probability of going jack and then ace. Okay, I want to go jack, then ace. But I'm not going to replace the first card. So if I don't put the first card back in the deck, how many cards are left in the deck? 51. So now that new probability is dependent upon the first one because the pool has changed. So 6. Now I only have 51 cards left to get my jack. I got 2. I still lost, but the idea here is that a dependent event is when one affects another. It's very easy to make that correlation because what's going on is that you have what they say without replacement. A lot of times that's kind of the key word there to figuring out if it's going to be a dependent or an independent event. If you read it, it's pretty simple to see. The way they write it is a little bit weird though. What they call it is a conditional probability. What that is read as the probability of B given A. That's what this symbol means. Probability of B given A. That means probability of B given that A has occurred. You've already used it. Yes, sir?
How would you do it when, say it said like, you draw a jack or a 4,
Mm-hmm.
and you draw twice, and you can't replace it? Would you have to know, because you have the chance of drawing one, but then you don't put it back in, so there's one less of it, so it'd be 7 out of it.
You're looking at, it's a great question. This came up earlier. What you're thinking of here is something that is well beyond the realm of what we're even bothering. Okay? What we're looking at is what's just the theoretical probability that the first card, what's the probability of getting that jack the first card, then what's the probability of getting the jack the second card without putting that first card back. You're not taking into consideration the possibility that you did get that. That is one of those more further out there statistical stuff that you can get into.
I just need it so I can count cards.
You know, I mean,
I count cards.
this kind of gets you towards the idea of counting cards. Now, yes, sir.
So for the independent one, even if you put the card back on top, how is that, like, it would still be 51 cards that you don't know if you're going to get another one.
I see what you're saying. Think of it as it's mixed back up.
Even though you're putting the same card back on top?
You're not putting it back in top, you're just putting it back in the pile.
Okay. So it's not how you did it, because that's you just...
Right, I just threw it in there, okay?
But the way they want you to see it is you just putting in random.
Yeah.
All right.
Now, what Hunter's getting at here is the idea of getting blackjack. So the probability of getting dealt 2 cards, boom, boom, blackjack. Blackjack is a black ace and a black jack.
Didn't Jack get blackjack?
I think he did.
What's the probability of that?
Not good. So if you want to think about the idea of getting dealt 2 cards and getting blackjack, that means in order to get the true blackjack, you'd have to get a black ace and a black jack. Now, it doesn't really matter which one comes first. And that's not going to really mess our theoretical probability for this to occur because there's still, however many aces and however many jacks in the hands. Now, how many black aces are in the deck of cards? There's 2 of them. So the probability of the first card being a black ace is 2 out of 52. I don't put that back in the deck, therefore how many cards are left to draw from? 51 of them. And how many of those would be a black jack? So now the probability of being dealt 2 cards and getting straight blackjack out of 2 cards is what? Whatever that number is, okay? How's that yellow calculator treating it? Good. Yep. The probability of that, the theoretical probability, is 1 out of 663. So, here's 2 cards.
Let's just do a 663.
Nope. 2 cards. No. 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 Oh, there's one of the blackjacks. We're dealing out.
Are we playing cards?
It's all about probability. Probability of being dealt 2 cards blackjack.
Mr. Hurst.
We're not doing. Oh, 2 jacks are gone now. Want to play again?
No, I'll just
Oh no, you're real fast. Billy in? Sure. Anybody else?
I'll go.
Come on. What do you want? I know. So does that make sense, the difference between independent versus dependent? Dependent means that something has already occurred. Now, from what I've understood from talking with the other classes, you guys probably saw independent, dependent problems when you were looking at socks in a drawer, marbles in a bag, pulling those out and replacing them without replacing them back in algebra. I'm hoping, right? So you've at least heard the terminology. You might not have just seen it written the way that we're looking at it. So again, basic idea here is we've kind of walked through these examples. You're going to select 2 cards from a 52 deck. Probability of the first card is not a face card, and the second card is a face card. We're going to go both ways. Show it as with replacement and without replacement. So we want to go with probability not a face card, and then a face card. We're going to do this 2 different ways. With replacement and without. See if you can figure that out real quick. Not a face card, and then a face card. And you go both ways with it. With replacement or without replacement. And this also came up earlier today about how your answers should be written. Probabilities are legitimate to be written as fractions, decimals, or percents. Either one of those is fine.
We count aces as face cards.
Now, face cards were always going to count as king, queens, and jacks. All right, so when you go not a face card, how many cards are not face cards?
40.
Yeah, one of the things here is this is a good time where we talk about not a face card where it's easy to use the complement. You know there's 12 face cards, so there's got to be 40 that aren't. So you've got 40 out of the 52. You're replacing, you're putting it back in the deck, which means that now there are 12 out of 52. So the probability of going not face card would be whatever this fraction is. What'd you get? 31 over what? And then the difference between that when it goes without replacement, not a face card, and then face card would be just the 12 out of the 51. So it's a little bit different. Okay? It doesn't really start to be making a huge, huge, huge difference until you start getting into, I don't know, you start to like lottery and things like that. So, questions at all? Let me give you some props. Bless you. For what? What do you mean? stuff quicker than this.
How is that still right now?
No, we've gone through a lot of. Like I said, today's stuff isn't.